So we have a physics PhD qualifying exam practice problem number 19 on domain of statistical mechanics. So let's begin. Consider an ideal gas of spin zero bosons in 3 dimensions. Part A. Starting from the ground, canonical partition function, derive the occupation number distribution n of epsilon. Okay, so this is a quantum ideal Bose gas and condensation problem. So for part A, the grand canonical distribution, the grand partition function is that capital Xi equals that capital pi, and then we have this sum of n sub k equals 0 to infinity of this ze to the negative beta epsilon sub k, that quantity raised to the n sub k. The geometric series here, capital Xi equals capital pi 1 over 1 minus ze to the negative beta epsilon sub k. Oh, by the way, sorry here for this component here, for capital Xi, this is where z equals e to the beta mu. Okay, so going back here was the geometric series. Sorry about that. So thus we have ln of capital Xi is equal to this negative sum k here, this ln of 1 minus ze to the negative beta epsilon sub k. The average occupation here is given, it's that expectation value, that n sub set k, that expectation value of n sub k equals negative 1 over beta. And then here we have this partial with respect to epsilon sub k, ln of capital Xi. So we could say, therefore, that n of epsilon equals 1 over e to the beta times the quantity epsilon minus mu, close parentheses, and then minus 1. And this is the Bose-Einstein distribution for letter A. Okay, for letter B, they want us to derive the density of states, G of epsilon for the system. So density of states, we'll just get this ready here. Sorry about that. Okay, sorry. So for here, density of states, the number of one particle states with momentum less than p is G of p equals v over h cubed, 4 pi p cubed over 3. And using h equals 2 pi h bar, we get G of p equals v over 6 pi squared h bar cubed, p cubed. Since epsilon equals p squared over 2m, p equals 2m epsilon to the 1/2, G of epsilon equals v over 6 pi squared h bar cubed times the quantity 2m epsilon to the 3/2. So the density of states is G of epsilon equals this derivative of G with respect to epsilon. So we get G of epsilon equals v over 4 pi squared times the quantity 2m over h bar squared raised to the 3/2 times that epsilon to the 1/2. So that's the density of states, G of epsilon for the system. For part C, they want us to derive the Bose-Einstein condensation temperature T sub C in terms of density. Okay, so condensation temperature, the number of excited particles is n sub ex equals this integral from 0 to infinity G of epsilon d epsilon over e to the beta times the quantity epsilon minus mu minus 1. Sorry. So at condensation, mu approaching 0, so n equals from 0 to infinity G of epsilon d epsilon over e to the beta epsilon minus 1. Substituting x equals beta epsilon. So then n equals v over 4 pi squared times 2m over h bar squared raised to the 3/2 times that k sub b t sub c raised to the 3/2, and then times that integral from 0 to infinity x to the 1/2 over e to the x minus 1 dx. So here, from 0 to infinity of this integral, x to the 1/2 over e to the x minus 1 dx equals capital gamma of 3/2 zeta 3 halves, zeta 3 halves, and this gamma 3 halves that equals square root of pi over 2. So we get here n equals this v zeta 3 halves, and then times this m k sub b t sub c over 2 pi h bar squared to the 3 halves. And equivalently, we have n equals capital N over v equals this zeta 3 halves over lambda sub t cubed. And isolating this lambda sub t equals h over square root of 2 pi m k sub b t. So what we're going to wind up with is T sub C, condensation temperature, in terms of density, that is going to equal 2 pi h bar squared over m k sub b times the quantity n over, that's zeta 3 halves raised to the 2/3. Okay, so that's letter C. For letter D, they want us to do, for T is less than T sub C. So for T is less than T sub C, derive the condensate fraction N naught over N. So for this one, so the condensate, whoops, sorry about that. Okay, so condensate fraction for T is less than T sub C. So for T is less than T sub C, mu equals 0, and the number of excited particles is N sub EX equals V zeta 3 halves, and then this M K sub B T over 2 pi H bar squared raised to the 3 halves. And using the definition of T sub C, N sub EX over N equals this quotient of T and T sub C raised to the 3 halves. So if we take this difference here, N naught equals N minus N sub EX. So N naught over N equals 1 minus the quantity T over T sub C raised to the 3 halves. Okay, so that's the condensate fraction, N naught over N. And for part E, what they want us to do is to they want us to derive the low temperature heat capacity and determine whether a discontinuity exists at T sub C. Okay, so let's see what happens here. For part E, low temperature heat capacity. So for T is less than T sub C, the internal energy is carried by the excited particles. U integrated from this integral 0 to infinity, epsilon g of epsilon d epsilon over e to the beta epsilon minus 1. And this is going to give U equals 3 halves k sub bt, v over lambda sub t cubed, zeta 5 halves. And since v over lambda sub t cubed equals n over zeta 3 halves, t over t sub c to the 3 halves, then we could say U equals 3 halves n k sub b t zeta 5 halves zeta over zeta 3 halves times that t over t sub c to the 3 halves. Okay, so now from there, U equals 3 halves n k sub b zeta 5 halves over zeta 3 halves t to the 5 halves times t to the 5 halves over t sub c to the 3 halves. So from here we have this c sub v equals this partial derivative of u with respect to t at constant v. So c sub v, that's going to equal 15/4 n k sub b zeta 5 halves over zeta 3 halves times that t over t sub c raised to the 3 halves. Okay, so building on that, so at that t here, that t equals t sub c minus, or t sub c from below, that's c sub v of t sub c minus, that equals 15/4 n k sub b zeta 5 halves over zeta 3 halves there. And numerically, that zeta 3 halves, that's about 2.612. that zeta 5 halves is about 1.341. And so that C sub V of that T sub C minus, that's about 1.93 N K sub B. And so we could say for T is greater than T sub C, the heat capacity approaches the same value at T sub C. So C sub V is continuous at T sub C. However, its derivative is singular cusp. So the ideal Bose gas has a non-analytic thermodynamic signature at the condensation transition. Okay, so that's all for this one. Thank you very much and have a great day.